Okay. Hello class, and welcome to Last Year Revisited. So since I'm going to be gone, I'm going to record you something. Feel free to stop it, rewind it, play it again. I'm going to say it really fast because I need it to be done short amount of time, but you might want to stop and pause and write things down. So first things first, looking here, we want to sketch a graph of a function with a removable discontinuity at 2, 5. And for the opener, you want to have is f of x equals sine of x increasing or decreasing at x equals 2. Go ahead and pause it now so I don't give away the answer, and a couple minutes later press play. So here's the answers to those. The answers are the fact that there is something at 2, 5, that there's a removable discontinuity. As long as there is a hole, if you can see that, at 2, 5. There's an open spot right there at 2, 5. The second one here is the fact that we're going to be going down. The sine function starts in the middle, will go up and go down. We know that. The question is, where is 2? And 2 is between pi over 2, which is 1.57, and pi, which is 3.14. 2 is somewhere in that region, and in that whole region, the sine graph is on its way down. It's decreasing. So the answer is, it will be decreasing. Okay? Our next thing is limits at infinity. We said we're going to add this to it. So limits at infinity are things that when I get off to the end. So pre-calculus, this is horizontal asymptote. Calculus, however, means I need to find a limit when it gets really big. So what we're going to do, if you look at pre-calculus, the degree of the denominator is 2, the degree of the numerator is 1. When I get to infinity, the denominator has more power, so it will be a big number, so it'll be relatively a little at infinity over a big, right? Because big squared, infinity squared is more than just infinity. All right, so that's the idea there. But how do we figure this out? We're going to do some fancy division. So what we will do is we'll divide the numerator by x squared, and we'll divide the denominator by x squared. Now you might ask, Mr. Lofstrom, you're slashing and that's not good. You're right, but if you think about this, x squared over x squared, if I think of this as the fraction, it's x plus 1 over x squared over x squared over x squared. Think about that. And what I've done by dividing them both by x squared, in essence, I've multiplied by the number 1. Okay? And now I'm going to be, instead of multiplying by the number 1, I'm going to go ahead and do division, and this is going to equal the limit as x approaches infinity of x over x squared is 1 over x plus 1 over x squared divided by x squared over x squared, which is 1. Now we're going to use this idea, and the only limit we're really going to use is a limit as x approaches infinity of 1 over x. By definition, that will be, we talked about yesterday, the last class period is little over big, and they're not even close. Little over big is going to be 0. Sorry about the glare on there. I didn't know how to get that off, but it looks like you might be able to read it, I hope. So, when I apply this limit, I apply the limit into the 3 different places. This thing will be, this equals, and I know this was kind of sloppy, and I don't want you guys to be that sloppy, but put an arrow there, put an arrow there. This equals, this limit evaluated is 1 divided by infinity, which is 0, plus 1 divided by infinity, which is 0 again, over the limit of 1 at infinity is still 1. So this is 0 over 1, so that limit is 0. And that makes sense because the denominator had more power, so it'll level off at 0. Because I'm in a hurry, here we go. We take a look at this. How do we do this? You want to read this. Let's say it real quick. You divide both the numerator and the denominator by the degree of the denominator, so the highest power of the denominator. Simplify, and then determine the limit of each, and then simplify those answers. So if I have this one right here, the limit as x approaches infinity, I identify that the degree of the denominator is x squared, so it's 2. So I divide everything by x squared. So my next statement will say, the limit as x approaches infinity of the 3x squared minus the 5x plus the 2, and that's all going to be divided by 8 minus 2x squared. And now each of those gets divided by x squared. Okay? So this becomes the limit, and I know I'm running out of board space, I'm also in a hurry. So this becomes the limit as x approaches infinity of 3x squared over x squared is 3 minus 5 over x plus 2 over x squared, and the denominator becomes 8 over x squared minus 2, just plain 2. Now I apply that limit, and this limit right here of 3 becomes 3. Limit of 5 over x, so that's 1 over x times 5. The limit of 1 over x is 0, and so that's 5 times 0, or you can just call it 0 if you want. And then 2 over x squared is 2 times 1 over x times 1 over x. And each of those limits of 1 over x is 0, so that's strongly in there as 2 times 0 times 0, not 200, but 2 times 0. And this is 5 times 0, over 8 times 0 times 0 minus 2. Which, when I clean this up, 3 minus 0, I'll do one extra step just so we can see it, plus 0 over 0 minus 2 becomes a negative 3/2. And we knew that in pre-calculus because the degree here is 2, the degree there is 2. Both of their coefficients should have some power in the horizontal asymptote. But this is how we prove it, because we call that a limit at infinity. All right? Quickly, do I have time for one more example here? We'll try for this one. If I have x to the 4th over x to the 3rd, we'll do what I don't want you guys to do, is to just write it out like this. Because I never know what the original problem was if you just kind of do that. But since I'm using 2 colors, maybe we'll save us a little room here. But on your papers for the test, don't do that. Rewrite it. And this x to the 4th over x cubed is x minus 2 over x cubed over 4 plus 3 over x squared plus 1 over x cubed. Now, I go ahead and evaluate each of those limits, and each limit there turns into, this is infinity, minus 0 over 4 plus 0 plus 0. And simplified, that's going to be infinity over 4, but when you divide infinity by 4, I'm sorry to tell you, this is still just infinity. And so, that limit does not exist, really, right? So, it's describing that it's going off to infinity, but it does not exist. So, there you have limits at infinity in a nutshell. Things that you want to look at then, what I added to it was 5, 5, page 363. Those numbers, 7, 9, 15, 19, 25, 27, 35. Add those to it. On day 8, these problems from the book, 1, 2, 3, and 5 through 19, and page 260, number 7, I looked through those again, those are all really good questions. A couple things to note is that 17 and 18, make sure you put it in terms of calculus. It's really easy because they're asking about vertical asymptotes, which I know is a pre-calculus idea, but we want you to talk about it in terms of calculus, that there's a limit, there's a vertical asymptote, and there's a limit, there's a one-sided limit that is unbounded, okay, that it goes to infinity. And then the same thing, 18, put in calculus terms. A couple of the questions ask you to discuss something. Well, that means you're going to write things out and explain why it's happening. And you're going to use definitions and things like that in calculus, of course. And then know when you can and when you can't apply the intermediate value theorem. Be sure you know when you can and when you cannot apply the intermediate value theorem, because you'll lose points if you try to apply it somewhere where it does not belong. And the last one is, know how to find a limit if I'm looking at a table, if I'm looking at a graph, or I'm doing it analytically, because I promise you that'll be there. So, look at this, study it, do what you need to do. Good luck. Send me emails if you need it. Hopefully my family will be healthy and I'll be back in